Welcome back to part 2. So in our part 1, we saw the periodic table and the element's properties, along with the review of Professor Mendeleev and his first periodic table. Now, these guys up here, like R2O, R2O3, what are those for, you might ask? Well, these guys are all just like based on valence electrons. For example, hydrogen and lithium all of these guys here have 1 valence electrons. In other words, they give away their 1 electron to oxygen and then they bond in, like H2O. RO is these elements with 1 oxygen. For example, calcium will most likely give away both of its electrons and bond with oxygen with CaO. Here, R2O3 and so on. But we can also see valence electrons in this periodic table. Group 1 has 1 valence electrons, Group 2 has 2, 13 has 3, 14 has 4, and so on. So it's kind of easy to get the P blocks and S blocks all sorted out. But what about these guys? In part 1, I said that these guys actually tricked Mendeleev all the way to the end of his life. In fact, palladium is also a big problem. So, the 3 to 11 elements are the ones that bother Mendeleev. Why is that? Well, Mendeleev said... So, Professor Mendeleev said that every single atom increases in terms of valence electrons from the inside in first and then to the outside. Like this model, for example. If this model was accurate enough, then potassium would go like this, then calcium, and then scandium would have had an electron configuration of this. But believe it or not, this is wrong for scandium. Scandium actually has an electron configuration of the normal, this part, but on the 3rd shell, he has 9 electrons. And 2 on the outside. For some reason, the outer electron did not go here, but actually ended up in the inner orbit here. You can actually go on and on by adding 1 by 1 electrons until you get to chromium. It looks like chromium's gonna have to look like this, right? Let me draw the electrons a little bigger so that you can see it. So here are the inner electrons of chromium. So it should look like this, right? Well, no. 1 of these electrons actually hop into the inner orbit and it looks more like this. And Mendeleev got kind of baffled. So, as you go on, copper will be the next weird element you get in the electron configuration. Because it's got 1 valence electron and a complete inner set. So it's going to have 18 electrons in the 3rd shell and only 1 in the 4th shell. But an even more baffling concept was that in our current periodic table, these numbers not only just state the rows, but the number of electron orbitals they have. So hydrogen and helium will have 1 shell, lithium, beryllium, and so on will have 2 shells, and so on. Palladium was the only element that actually broke this rule. Palladium actually has an electron configuration of electron orbitals of 2, 8, 18, and another 18. Palladium is a row 5 element, but it only has 4 shells. 1, 2, 3, 4. Strange, right? Now, let's see how we write electron configurations. First of all, we gotta know the blocks. What are the blocks? Well, the blocks are, well, you can just think of it like this, but helium is an S block element, so, well, instead, I'm gonna have to draw it like this. Hydrogen, helium right next to each other. Helium is on top of the alkali earth metals. Hydrogen is on top of the alkali metals like usual, and so on. So these are the S block elements. And the next one you'll ever encounter in your life are the P block elements. So boron, carbon, nitrogen, oxygen, fluorine, neon. And then you go back to the S blocks. Sodium, magnesium. So let's just say you got to potassium and calcium. Wait, where's scandium again? Scandium is a D block element, meaning that it's completing its D shell. Oh. So it's gonna have one D. So titanium and so on will also be D blocks. All the transition metals and zinc, cadmium, mercury, and copernicium are D block elements. What about the lanthanides, Ln, and actinides, An? Well, they're going to be F block elements, so there'll be 4 blocks on the periodic table. We write electron configurations the long way, so the number, row number, and then block, and then on the superscript, we're going to have the number of electrons. I'm going to abbreviate it as E. For example, hydrogen has an electron configuration of 1s1. Helium would be 1s2, and so on. But then, once you go on to lithium, things are going to change. Now you're on row number 2, so you're going to 2, and it's in the S block, and then 1. But what about, let's say, nitrogen? Nitrogen will not have this configuration. Remember, it's a P block element. It needs a P electron. In fact, only 2 electrons are allowed to go into the S orbitals. So, it's going to get a 2p orbital, and then it's 1, 2, 3, so 3 in the electron configuration. This will be N. What about other elements? Say, what should I do? Oh, vanadium. Vanadium has 1s, S2, 2s2, 2s6. That's a complete neon. And then 3s2. And then you're gonna have the 3p6, 4s2. And then you're gonna get to 3d, what was it, 3. But you can also switch the orders between them, it doesn't really matter. Also, but this is way too long, right? You can't memorize it all in your head. So, we use a simpler method. 1s2 is the same electron configuration for helium. So we're going to get rid of this and put helium inside brackets. And then this configuration is the same for neon. So we're going to get rid of all of this stuff. And then put neon in brackets. These are the argon's electron configuration. So we're going to put argon inside brackets. Now we don't have any noble gases before vanadium anymore. Because vanadium, if you go back in terms of numbers, the first element you're ever going to hit is argon. But, let's say I switch vanadium with another element, say cadmium. Cadmium will have an electron configuration, well, 3d10 because it's a full set. And that'll be it. Cadmium has an electron configuration similar to that of krypton, not argon anymore. So cadmiums will be this. Let's try it out for an F block element. And let's try an F block element, say cerium. If you go back in numbers, the first noble gas you'll hit would be xenon. And then it's got a complete S set, so 6s squared. This is not a squared, it's a number of electrons. And then you're gonna have a 4f. Remember, it's a 6f electrons. So cerium would be, lanthanum is the first one, so lanthanum would have 1, and then cerium would have 2. So cerium's electron configuration would be xenon 6x is to the second power and 6f to the second power. Now, what about these? What about the transition metals? All of these guys actually baffle Mendeleev, which is right here. Thanks for watching. Never mind. So, there are elements that, in summary, there are elements, which are right over here, that, tricked Mendeleev all the way to the end of his life. And then, there are also blocks on the periodic table. You're never really you don't really know this, but are already separated for you. And also, you learn how to write electron configurations. Thanks for watching. Bye. And see you in part 3.